Good morning, everybody, and welcome to a slightly different format for Cameras and Coffee today. We're going to be playing 10 questions with Chat GPT to find out whether or not Chat GPT can teach us photography. But first, the intro. Okay, right off the bat, before we get started, today's coffee is Counterculture, the 46. It's a blend. Blends always have an uphill battle with me, but as blends go, it's a pretty good one. So thank you for the suggestion. I just wish I could remember who suggested it. I should have written that down. Okay. So in today's Cameras and Coffee, Chat GPT has been all over. Obviously, it's an important advancement in AI technology and the way that humans interface with technology specifically. AI in general has been around for a long time. That's not new. What is new is the way that AI can generate answers based on prompts. And it's a significant advancement in the way that AI works. So in today's video, we're going to ask ChatGPT 10 questions about photography. I can answer all of these questions, so I'll be able to tell you whether or not ChatGPT gets them correct. I ordered them in kind of an easiest to hardest order. They're linked in the video's description below, so you can read the questions, and if there's one you're specifically interested in, you can click right to that and see how GPT answers. And so I'm just going to type in the answers and put in the responses. And we'll look at the responses ChatGPT generates. Okay, so for our first question, I'm going to ask, please explain the photographic exposure triangle. Now, in a nutshell, the exposure triangle is, if you've seen this on a dry erase board, it's your sensitivity, which is your ISO, shutter speed, and aperture. And when those three things are in balance, you have a nice equilateral triangle and you have a proper exposure. But if one of those gets out of balance, you either have an overexposure or underexposure, too long or too short a shutter speed, too long or too wide or too small an aperture, or too fast or too slow of an ISO. So that's the triangle. And so I'm asking ChatGPT, please explain the photographic exposure triangle. Certainly. The photographic exposure triangle is a concept that explains how three key settings on your camera work together to determine the exposure of your photo. These settings are 1. Aperture. This refers to the size of the opening in the lens that lets light into the camera. The aperture is measured in f-stops, and a larger aperture, lower f-stop, will let in more light than a smaller aperture, higher f-stop number. 2. Shutter speed. This refers to the amount of time that the camera's shutter is open, allowing light to hit the camera's sensor. The shutter speed is measured in fractions of a second, and a faster shutter speed will let in less light than a slower shutter speed. ISO. 3. ISO. This refers to the camera's sensitivity to light. The ISO is measured in numbers, and a higher ISO will make the camera more sensitive to light, allowing you to use a faster shutter speed or smaller aperture in low light settings. These three settings work together to determine the exposure of your photo. For example, if you want to let in a lot of light, you could use a larger aperture, slower shutter speed, or higher ISO, and that last part is wrong, by the way, and we'll get back to that in a second. On the other hand, if you want to let in less light, you could use a smaller aperture, faster shutter speed, or lower ISO. Again, wrong. On a technicality. It's important to balance these settings to get the desired exposure while also achieving the depth of field, motion blur, and noise level that you want in your photo. So I called out two of those statements in that paragraph as wrong, but the question is, why did I say they're wrong? The answer from ChatGPT indicates that a higher ISO or higher sensitivity or a lower ISO or lower sensitivity affects how much light is let into the camera, and that's not strictly true. ISO is simply or sensitivity is a number that is used to determine the amount of light that's needed to create a proper exposure. So the sensitivity will determine the length of shutter speed timing or the size of the aperture needed. ChatGPT got both of those right, but nothing intrinsic to the sensitivity itself will necessarily result in more or less light being let into the camera. You could have a 1/100th of a second shutter speed, and whether you're at 100 ISO or 1000 ISO, the same and the same aperture in this situation, the same amount of light is going to reach the sensor or the film. The difference is whether or not you have a proper exposure or something that is way over or way underexposed. So sensitivity doesn't have an effect on how much light reaches the imaging medium. It has an effect on how much light is needed in order for a proper exposure to be given with that imaging medium. Next question. What does it mean to push film? Pushing film refers to the process of intentionally underexposing a roll of film and then compensating for it during development by increasing the developing time. This technique is used when a photographer needs to shoot in low-light situations or when they want to achieve a specific effect, such as increased contrast or grain. When you underexpose a roll of film, the image will appear darker than usual. By increasing the development time, the film becomes more sensitive to light, which results in a brighter and more contrasty image. For instance, if you shoot ISO 400 film but set your camera to ISO 800, you're effectively underexposing the film by one stop. To push the film, you would compensate for the underexposure by increasing the developing time by one stop. It's important to note that pushing film can also result in increased grain or noise, so it's not always the best option for achieving a desired effect. Additionally, not all films can be pushed, so it's important to research the film you're using to determine if it's compatible with your pushing. Okay, so I'm going to say that this is mostly a correct answer. I'm going to take issue with one thing that Chat GPT said, which is that pushing film increases its sensitivity to light. And I would take a different stance, that nothing inherent to pushing film, to underexposing the film, or to the way it's developed, increases the sensitivity of the film to light. What happens when you increase the developing time is you increase the number of film grains that are developed. So if you take a roll of film and you shoot half of it at 400 and half of it at 800, using these examples, and it's a 400 ISO film, but you develop it for 800, all of those 400 ISO shots are going to be much darker than they should be on your negative. Not because the film itself has become more sensitive to light, but because more of the silver grains in the emulsion have been developed. So part and parcel to this is the way that film develops when it's in the chemistry, which is to say that highlights develop first and shadows develop last. So what happens when you push process film is functionally your film is now all shadow. It's all going to be thin and underexposed like a shadow area of an image if you just developed it normally. So by developing it for longer, you've basically taken all of that, what is functionally shadow data, and pulled it into the midtone, right? All of the midtone data functionally becomes highlight data. And so the longer it stays in the chemistry, the more that you're going to push the film towards an exposure that looks like all of the film reached its Dmax. So it's not that the film itself has, to say that the film has become more sensitive to light is fundamentally incorrect, because the developer doesn't change the properties of the film itself. The developing chemistry works with the emulsion of the film to pull out the images in different ways depending on time, temperature, specific chemistry, concentration, many different factors like that. So mostly correct, but part of the nuance was wrong. So let's give it another try, another crack at the bat here, and ask it about pulling film. Pulling film refers to the process of intentionally overexposing a roll of film and then compensating for it during development by reducing the developing time. This technique is used when a photographer wants to achieve a specific effect, such as reducing contrast or minimizing grain. When you overexpose a roll of film, the image will appear brighter than usual. By reducing the developing time, the film becomes less sensitive to light, which results in a darker and less contrasty image. For example, if you shoot with ISO 400 film but set your camera to ISO 200, you're effectively overexposing the film by one stop. To pull your film, you would compensate for the overexposure by reducing the developing time by 1 stop. It's important to note that pulling film can also result in reduced contrast and saturation, so it's not always the best option for achieving a desired effect. Additionally, not all films can be pulled, so it's important to research the film you're using to determine if it's compatible with pulling. So I'm not going to pop back to the camera for this one because this is basically going to get the same criticism I just gave for pushing film, with the caveat that, well, not a caveat, but with the further explanation that basically what we're doing is the opposite, right? Instead of taking all of those midtones and putting them into the shadow tone range when we push film, by pulling it, we're taking all of those midtones and turning them into highlights. Highlights develop more quickly in the developing chemistry, and so we develop those highlights for less time with pulled film, and that allows us to get a less contrasty image. So basically, we get less contrast because the everything is getting closer to the density max of the film more quickly, and by developing it for less time, then there's less variation in tonality between what is overexposed and what is underexposed, or what is shadow and what is highlight, well, vice versa, in the scene. Fourth question. This is where they're going to start to get a little bit more technical. Wait till you guys see the 10th one. Question 4. How does a camera lens focus light? A camera lens is designed to focus light by bending it using a curved piece of glass known as an optical element. The lens has multiple optical elements that work together to control how the light enters the camera and how it focuses onto the camera's sensor or film. When light enters the lens, it passes through the front element, which refracts the light and changes its direction. As the light moves through the other elements of the lens, it continues to bend and converge, ultimately forming an inverted image of the scene being photographed. The lens then adjusts the focus of the image by changing the distance between the optical elements. This allows the lens to adjust the position of the image on the sensor or film, resulting in a sharp and focused image. There are 2 main types of lenses: fixed or prime lenses, which have a fixed focal length and can't zoom in or out, and zoom lenses, which have a variable focal length that can be adjusted to zoom in or out on a subject. Both types of lenses use the same basic principles of focusing light through optical elements to create a sharp and clear image. So I kind of hemmed and hawed at part of that answer. And the part that I hemmed and hawed at was the third paragraph. This lens then adjusts the focus of the lens then adjusts the focus of the image by changing the distance between the optical elements. This allows the lens to adjust the position of the image on the sensor or film, resulting in a sharp and focused image. I disagree with the technicalities of that second sentence, because it's not that the lens is adjusting the position of the image on the sensor or film. What's happening is that the lens is adjusting the focal plane of the converging light on the sensor or film. So you'd think I'd have a lens ready to go for this. Here we go. So we've got the lens right here, okay? And the light comes in to the front of it and gets bent out the back of it, reversed, of course, as you know, and then is projected onto the film plane. When we focus the lens, the front element and the whole of the lens assembly in a traditional lens like this one moves in and out. So the front element here is moved out, let's call that 15 millimeters. The rear element has moved inward to the lens 15 millimeters as well, okay? So what happens is that infinity focus, this is a 100 millimeter 2.8 lens. Infinity focus on this lens, if it were a traditional lens, would be 100 millimeters from the lens, the nodal point, to the imaging sensor or film plane, whichever it may be, okay? And that never changes. If you move the front element out 15 millimeters and now you're focused at 7 feet away instead of infinity, you would have the exact same effect as if you took the film and you moved it back 15 millimeters and did nothing with the lens. Nothing about the lens's movement changes the position of the image on the sensor. It changes the position of the focal plane of what is in focus on the from the lens on the sensor. So I'm gonna take issue with the technicalities of the way that that one sentence was worded and say that it's not technically correct, but that it does sound like whatever Chat GPT learned from to give us that answer was trying to get to the right answer. All right, let's go to question 5. Wow, we're just cruising through this, aren't we? How does a digital camera sensor create an image? And what I'm looking for this basically is an explanation of the pixels receiving the light, converting it into a digital signal that's then converted into an image by the computer processor. A digital camera sensor is made up of millions of tiny light-sensitive pixels that work together to capture and create an image. Each pixel on the sensor measures the amount of light that hits it, and this information is then used to create the final image. When you press the shutter button on a digital camera, the camera shutter opens and light enters the camera through the lens. The light is then focused by the lens onto the sensor. Order of operations is wrong there, but it's not inaccurate. Anyway, where each pixel records the amount of light that hits it. This creates a digital representation of the scene being photographed. The sensor then converts the light into an electrical signal which is sent to the camera's image processing engine. The image processing engine takes the data from the sensor and applies various settings such as white balance, exposure, and color correction to the final image. The final image is then saved onto a memory card, either in a JPEG or RAW format, depending on the settings chosen by the photographer. JPEG files are compressed and processed by the camera, while the RAW files are unprocessed and contain all of the data captured by the sensor, giving the photographers more flexibility to edit the image later on. Overall, digital camera sensors work by converting light into electrical signals, which are then processed to create a digital image that can be saved and shared. And no need to go back to the camera. Honestly, that answer is good. Aside from the one order of operations issue in that one paragraph about light reaching the sensor and then going through the lens, the rest of that is pretty much spot on for what I was looking for in terms of an answer. Question number 6. Why does a lens focal length affect the angle of view of an image? And basically, this could be a really nuanced and difficult answer. It could talk about image circles, different formats, but in essence, what I'm looking for is the fact that a longer lens has a longer infinity focus point, and that infinity focus point will cause that if you have the same size image area, that basically what's going to happen is that longer focus point projects less of the scene because infinity is starting further, infinity starts off closer, or further out rather, with a longer lens than with a shorter one. The focal length of a lens affects the angle of view of an image because it determines the magnification of the image and how much of the scene will be captured in the frame. That's a very good start. The shorter the focal length, the wider the angle of view. This means that a lens with a short focal length will capture more of the scene in the frame, allowing you to see a wider angle of view. A wide-angle lens, for example, typically has a focal length of 28 millimeters or less, and it can capture a large part of the scene in a single shot. Conversely, the longer the focal length, the narrower the angle of view. This means that a lens with a longer focal length will magnify the image, making it appear closer and smaller, while also capturing less of the scene in the frame. A telephoto lens, for example, typically has a focal length of 70 millimeters or more and can be used to capture distant objects or portraits when you want to isolate the subject from the background. Therefore, understanding the relationship between the focal length and angle of view is important when choosing the right lens for a particular situation. For example, a wide-angle lens is ideal for landscape photography, while a telephoto lens is better for capturing portraits or wildlife. Okay, so this is another one that I would rank as mostly correct. In fact, if Chat GPT had just stopped after that second line, I'd have been happy with the answer, because I was trying to get to the word magnification when I said what I wanted the answer to say, and it went straight there. So basically a long lens, we'll call that a short 0 millimeters, whatever, shortest. 0 millimeters is impossible, but you get my point. Short lens, long lens, okay? The higher the millimeter number, the longer the lens is in traditional lens engineering technology or design, right? So a long lens basically basically takes a smaller part of the scene and projects it onto the same image area, magnifies part of the scene more than a wide-angle lens. So the first two lines, great. The last paragraph, also okay. Those two middle paragraphs that it gave, complete junk. They don't answer the question of why. They basically just talk about the effect. So basically, they're not technically wrong. They're just missing the mark on the nature of the information the question was going for.
Okay, so that is what, question 6? Yeah, question 7. Why does closing a lens aperture increase the depth of field? Basically what I'm going for here is some sort of answer that talks about the light passing through the middle of the lens being more in focus than light passing through the outside of the lens. Choosing a lens aperture increases the depth of field because it reduces the amount of light that enters the lens, which in turn increases the range of distances in the scene that will appear in focus. I'm going to take issue with that paragraph. When a lens aperture is wide open, only a narrow range of distances in the scene will be in focus, which is known as a shallow depth of field. This can be useful for isolating a subject from the background or creating a blurry background, but it can also result in parts of the image being out of focus. By closing the aperture, you reduce the size of the opening through which light enters the lens, which increases the range of distances that will appear in focus. This is because a smaller aperture increases the area of the lens that is in focus, creating a larger depth of field. I do not like this answer. However, it's important to note that closing the aperture too much can result in diffraction, which can also reduce the overall sharpness of the image. Therefore, it is important to find the right balance between aperture size and depth of field for a given situation.
I don't like that answer at all. In fact, there are some things in here I think are just factually wrong. All right, when a lens aperture is wide open, only a narrow range of distances in the scene will be in focus. Correct. Which is known as a shallow depth of field. Fine. Doesn't answer the question. This can be useful in isolating subjects from the background. Fine. This is all off topic. By closing the aperture, you reduce the size of the opening through which the light enters the lens, which increases the range of distances that will appear in focus. Fine, that's correct. This is because a smaller aperture increases the area of the lens that is in focus. What? What? Increases the area of the... Okay, I think what it's not using the right words. I think it's a problem. I don't think that's... Anyway, I'm not going to give it that. That's not right. All right, so let's go up to this first paragraph. Closing a lens aperture increases the depth of field because it reduces the amount of light that enters the lens. Wrong. Wrong. The amount of light passing through the lens, and it shouldn't be entering the lens. The same amount of light enters the lens in the same scene. It's how much gets blocked by the aperture. But the amount of light passing through the lens in and of itself has nothing to do with depth of field. What that sentence would imply is that if you take a 100-watt light bulb and you point it at a lens, you're going to have more depth of field than if you take a 40-watt light bulb and point it at the lens. So that sentence is wrong. So reduces the amount of light that enters the lens, which in turn increases the range of distances in the scene that will appear in focus. Okay, so basically here's the way that a lens works. If you imagine the cross-section of a very simple lens, right? It's kind of like oval shaped. Each of the surfaces of the lens are partial surfaces of a sphere, all right? And this is why, like, when aspherical lenses, that surface is not part of a sphere. But if you take two surfaces of a lens, whether they're like a biconvex or a biconcave or a meniscus lens, whatever combination you have, each of those two surfaces can be defined as the arc angle of that surface being part of a sphere which is larger than that lens, okay, unless you get into spherical lenses outside the topic of this video. Anyway, so what happens when you take a lens, the light up here at the very top reaches a different part of that arc and has to focus, and it's bent a lot. So the bending of the light is going to cause it to go out of focus. In the center, the very center rays of light pass through unimpeded, straight through, okay? And so basically the light that's in the center, because it bends less, isn't affected by, the focus isn't affected by it. That something to that effect is what I would have liked to have seen, which basically says that shutting the aperture restricts the peripheral light rays from reaching the film, and those peripheral light rays are less well focused than the central light rays.
Question number 8. How does black and white photographic film record light? Basically what I'm looking for here is an answer that talks about silver halide grains, and that silver halide grains have a property which intrinsic to them, which records light at a certain rate. So silver halide grains themselves are sensitive to light at a known sensitivity. And black and white film, it doesn't have to go into this much detail, but for your own edification, black and white film uses different sensitizing dyes to effectively increase the light spectra that silver halide grains can record, and also the sensitivity to those spectra. But the gist of what I want here is something about silver halide grains being sensitive to light, and then the suspension and the emulsion and the grain size or whatever like that, affecting how sensitive the film is. Black and white photographic film records light by using a light-sensitive emulsion that is made up of silver halide crystals suspended in a gelatin coating on a plastic film base. When the film is exposed to light, the silver halide crystals absorb the light and undergo a chemical change. This chemical change creates a latent image in the film which is not visible until the film is developed. During the development process, this film is treated with chemicals that convert the exposed silver halide crystals into metallic silver, which is visible as black areas on the film. The underexposed silver halide crystals are then removed from the film, leaving behind the developed image. The amount of silver that is formed on the film is directly related to the amount of light that has hit the film during exposure. This means that areas of the image that received more light during exposure will appear darker on the developed film, while areas that received less light will appear lighter. Black and white photographic film can be manipulated during the development process to create different effects. For example, adjusting the development time or strength of the chemicals used can alter the contrast and tonality of the final image. Additionally, different types of film have different sensitivities to light and can produce different levels of grain or texture in the final image. So I'm going to give Chat GPT that was a good answer. In fact, I think that answer in a lot of ways was better than what I came up with off the top of my head as it started typing. So yeah, that was very well done on its part. All right, question number 9. If the same camera lens is used at the same focus point and same aperture on 2 cameras, one full frame and one micro four thirds, will the depth of field be the same in both images? And the answer here should be yes. It's just that the amount of image recorded will be different. Okay. No, the depth of field will not be the same in both images if the same lens is used at the same focus point and aperture on a full frame and micro four thirds camera. Ooh, that's wrong. And we'll talk about that in a second. The reason for this is that the sensor size of the 2 cameras is different, and this affects the way the image is captured by the lens. Also wrong. A full-frame camera has a larger sensor than a micro four thirds camera, which means that it captures more of the scene and produces a shallower depth of field for a given aperture and focal length. No. To achieve the same depth of field on a micro four thirds camera as on a full-frame camera, you would need to use a smaller aperture or a shorter focal length. Oh, disappointing, because this should be common knowledge. This is because the smaller sensor size on the micro four thirds camera increases the effective focal length of the lens, which in turn affects the depth of field. So if you want to achieve the same depth of field on both cameras using the same lens, you need to use different settings on each camera to compensate for the differences in sensor size.
All right, let's talk about why that's so wrong. Depth of field is not affected by sensors. Period. End of story. Now, I know as of this video going live, I have not yet released my crop compare video. It's on the calendar. It was on the calendar. Where'd I move the flag? Anyway, okay, so basically I have done a video taking a full frame sensor, an APS-C sensor, and a micro four thirds, two lenses, both of them the same, used on all three cameras, taking the three cameras, reshooting the same scene from the exact same position to show how the crop factor affects image area, and then reframing the images with each camera of the smaller sensor to recreate the large format, or the full frame rather, image as close as possible on the smaller sensors. So I will give you a spoiler alert for that video right now. What it demonstrates is that at the same camera position, depth of field does not change across the different image sensors, which stands to reason because depth of field is a function of your lens's focus point and your aperture, not the sensor size. Now, what this is going for and not getting anywhere close to is that apparent depth of field is going to change, and there are two reasons for that. If you recompose your image with the smaller sensor to get the same image composition as with your full frame sensor, you're going to be further away from your subject. The further that your lens is focused out towards infinity, the greater your depth of field is at each aperture. And if you don't believe me, grab an old lens that has focusing scales on it, line up your infinity with your f/16, and okay, infinity to f/16 on this 100mm 2.8, everything from 30 feet, which is 10 meters, to infinity is in focus. But if I scroll this thing all the way to the point where 1 meter is on the f/16 mark, I've got less than 1/10 of a meter of depth of field at the near closest focus point with this lens at the same aperture. So focus point and aperture setting determine depth of field, not sensor size. And so that's just straight up a failing grade on that answer.
All right, let's do our last question. Please explain how to read an MTF chart. Basically, I'm looking for an explanation about how the MTF chart measures sharpness with different contrasts going from the center of the sensor out towards the edges. MTF, modulation transfer function charts, are used to measure the sharpness and contrast of a lens at different frequencies and distances from the center of the image. The MTF chart displays the lens performance as a graph, with the horizontal axis representing the distance from the center of the image, and the vertical axis representing the contrast or sharpness of the lens. That's good. To read an MTF chart, you need to understand the two sets of lines that are shown on the graph. Solid lines represent the lens performance for contrast, while dotted lines represent the lens performance for sharpness. These lines are typically color-coded, with blue representing the performance of the lens at the center of the image, and red representing the performance of the lens at the edges of the image. The MTF chart is typically divided into 4 quadrants, with the upper left quadrant representing the lens performance at the center of the image, and the lower right quadrant representing the lens performance at the edges of the image. The other 2 quadrants show the lens performance at various distances from the center of the image. To read the MTF chart, you can look at the points where the contrast and sharpness lines intersect the horizontal axis. These points indicate the distance from the center of the image at which the lens reaches a specific level of contrast or sharpness. For example, if the contrast line intersects the horizontal axis at a distance of 20 millimeters, that indicates that the lens has a contrast of 50% at a distance of 20 millimeters from the center of the image. In general, a lens with higher MTF values on the chart will produce sharper and more contrasty images. However, it's important to note that MTF charts are just one tool for evaluating lens performance, and other factors such as distortion, chromatic aberration, and bokeh, I hate that word, should be considered when choosing a lens.
I'm not going to lie, I expected that answer to be the one that Chat GPT would get the most incorrect, not number 9. I think it did really well on that answer. I was unaware of the color coding, the red and the blue, and when it talks about using quadrants, that's curious. So my understanding of an MTF chart, and maybe I'm wrong on this, and somebody who knows more about MTF charts watching this video than me will correct me, but I always thought that it was center of the image here, and then edge of the image here, and then this directly related to sharpness, the shape of the lines, sharpness and contrast up here. I've never read about an MTF chart being broken into quadrants, unless what this is saying is that what we ever see of an MTF chart is just 1/4 of the full MTF chart. I'm not sure if that's the case, if that's what it's trying to say. Some of what this answer is a little bit strange, but overall, like, it hit all the notes I was going to look for, and I would be pretty happy with getting that answer. So I'll tell you what, let's do one more bonus surprise question, and then we'll wrap this video up.
Bonus question: who is the best photography YouTube personality to learn photography from? If he doesn't say David Hancock, I'm going down to OpenAI and unplugging it. Oh, good Lord. Really? You're going to go with these? Oh, my God. Okay, he's fine. Thomas Heaton's good. Peter McKinnon's good. Okay. 2 of 5. Still a failing grade on that one. Thank you, everybody, for watching, and I'll see you in the next videos.